All right, so that's it. We are recording. Okay, everyone. So thank you so much for coming today. This is the final installment of the philosophy seminar at UQ for this semester, and it's my great pleasure to have Professor Scott Weinstein from the University of Pennsylvania. And Scott, of course, he has a very distinguished career as a logician. He's, in fact, the only, as far as as far as I know, the only student of Saul Kripke that actually got a PhD, which is very impressive. And he himself has done numerous contributions to the areas of logic and computer science, finite model theory, modal logic, intuitionistic logic. So it's a great pleasure for me to have him here. And Scott is going to be talking about the complexity of the set of validities of a theory. So please, Scott, take it away.
Great. Well, thank you so much, Guillermo, for inviting me. This is it's a great pleasure to have the opportunity to present this work. And thanks all of you who've turned out to the seminar today. I really appreciate it. So, as Guillermo said, this is work that I've done jointly with Dennis Hirschfeld, who's a professor at the University of Chicago in mathematics, and my mathematics colleague here, Henry Tausner. And and as Guillermo said, this is about the complexity of the set of validities of a theory, and we should understand at the outset what does this even mean. So the thought is there's the notion of the logic of a theory, and we might think, well, logic is logic, it's universal, and so what are you talking about, the logic of a theory? But on the other hand, you might think that, the logic of various, might differ from, let's say, one subject matter to another. And so this is, the idea. And we might think, well, there might be a different logic for geometry, and another logic for arithmetic, and another logic for something else entirely. And I choose geometry and arithmetic with a forethought. That the books of Euclid on geometry, and there were the books on arithmetic. And as we know, in the 20th century, the things turned out very differently for geometry and arithmetic. That is, famously, geometry is, decidable via the work of Tarski on real closed fields. On the other hand, famously, arithmetic, and even that tiny fragment of arithmetic that the ancients were so concerned with, namely the question of solvability of various Diophantine equations, as a general question, turned out to be undecidable, through the work of Hilary Putnam, Matiasevich, Davis, and Robinson. So maybe these different subject matters have different logics for all we know. Okay. So anyway, that's so the first thing that we'll want to do is explicate what we mean by the logic of a theory. And who knows, maybe some theories, it was a great disappointment, at least to some people like Hilbert, that validity for first order logic would turn out to be undecidable. But maybe the logics of some theories could be decidable. And well, anyway, we'll get around to that. Okay, so what we'll do in our analysis is focus on decidable theories. So as I say, we're familiar with many of those. Perhaps the most famous is the theory of real closed fields. But there are a lot of others. There's the theory of the rational numbers, the theory of arithmetic with just the successor relation. So there's all sorts of there are all kinds of decidable theories, and we'll consider the logics of these theories. And in fact, we will give a complete analysis of the logic of all decidable theories, and that analysis will proceed via a model theoretic distinction. So first, we'll look at omega categorical theories, and that will give us one set of answers. And then on the other hand, we'll look at non-omega categorical theories, and that will give us a different kind of answer. Okay, so then we'll transition to talking about constructive validity and VDEC, which is just shorthand for the collection of first order formulas that are in this sense, valid in all decidable theories. So that's the next thing. And there we actually resolve a problem that was left open by Robert Vaught in a 1960 JSL paper called, formulas true in all constructive models. So we'll connect up this notion of validity in decidable theories with various notions of constructive validity. Okay. And then finally, in a coda, uh, I'd like to talk about a formalism-free and machine-independent characterization of decidable structures. That is, uh, structures whose first-order theory is decidable. And this has a rather different flavor than the preceding sections, but it's something that I'm particularly keen on and felt like sharing, and it's something that I think is of considerable interest in light of various philosophers. Preoccupation with the notion, I mean, and appropriate, I shouldn't say preoccupation, I should say, focus and attention to the extremely important notion of formalism freeness. And here I have in mind especially a wonderful book by Juliet Kennedy called Gödel, Tarski, and the Lore of Natural Language, which really contains a deep and sustained study of the notion of formalism free and its importance in both 20th century and contemporary logic. So there you go. Okay, so that's the overview. And yeah, it occurs to me, and now that I'm looking at the time, that it's extremely likely that I will not talk about all of these subjects. So I think at some point I will rush to the coda, to the decidable structures, just because I would hate to miss that out. Anyway, okay. So uh, here we go. So what do we mean by the validity of what we mean by validity, of course, in general, is the usual notion. Formula is valid. Uh, first order logic. Now that's the only logic we'll be looking at. First order logic, just in case it's satisfied by every structure whatsoever, and we'll denote the class of the set of valid formulas by V. And in general, we'll just be thinking of some fixed finite signature, and typically it will be adequate just to think of the signature consisting of a single binary relation, the language of graphs, so-called. But here, when we talk about validity, as you see, we'll think of this as a schematic language, and in particular, we'll think about the language without identity. So what in older terminology people called the pure predicate calculus without equality. So anyway, that will be our main focus. But here, we just have the central theorem of logic, that is this the collection of validities is a sigma one complete set, and that is it's some people sigma. I should actually before I get too far into this, is the terminology sigma one, pi one, all of that a familiar uh, manner of speaking, or should I say something about uh, these notions that um, uh,
From the audience I see, it should be relatively familiar. But guys, if you don't know what this means, please speak up, and then Scott can definitely clarify. You can
okay.
just say a line in the chat, and yeah.
Okay, I'll proceed. Just with, until when and until anyone has questions about anything. Okay, so this is, as I say, what I think of as the one of the central results of mathematical logic of the 20th century. That V is sigma 1 is essentially Gödel's completeness theorem, 1930, and that it's sigma 1 complete, meaning a most difficult to compute sigma 1 set. That's essentially the result of church touring. So good. Okay. So now, what do we mean by the in this setting, we're going to be looking at formulas, as I say, first order logic without identity in some language with a schematic letter X of arity N, and we'll have a formula in some other language, and we'll look at the substitution of that formula in the schema. Okay, so that's just notation. And here's an example, which I think it's clear enough what the idea is. And of course, we'll allow for simultaneous substitution of uh, you know many formulas in a schema with many different uh, letters of different arities. Okay, so now we have the central definition around which everything else turns in the paper. That is, if we have a theory in a given language, which I say is in older terminology would have been called an applied predicate calculus. Oh, how did that happen? Yeah, and an applied predicate calculus. Then we look at uh, the substitution instances of a schematic formula in that language, and we say that this schematic formula is a validity of the theory just in case every instance, every substitution instance of that formula is provable in the theory, or as a theorem of the theory, or if we think of the theories as deductively closed, is an element of the theory. And we write V of t for the validities of t. Okay, so good. So it's clear that validity in general, the usual set of validities is a subset of the validities of T for any theory T. Uh, and it's well known that identity holds for some recursively axiomatizable theories. That in particular is the famous Hilbert-Bernays completeness theorem that the validities of piano arithmetic are exactly the ordinary validities. And in fact, essentially in Hilbert-Bernays, but more explicitly in Kleene's Introduction to Metamathematics, um, it was established that any schema that is not valid, that there's delta 2 formulas of arithmetic such that that substitution instance is not provable in PA. So that gives us this identity above. And I like to mention that there's a really great new proof of this result is given by Gary Epps and Warren Goldfarb in first order logical validity and the Hilbert-Bernays theorem. And among the many virtues of this paper is a new proof of the weak Koenig infinity lemma based on an idea from Skolom's work in 1923. So this is a really fascinating paper that also gives application of these ideas to Quine's thinking about substitutional, logical validity as substitutional validity. So definitely worth reading. Okay, but so we know that there are theories that give us back just the ordinary collection of validities as the validities of their theory. Okay. But then we might ask ourselves, well, of course, famously, piano arithmetic is not decidable. Is there any decidable theory that yields the usual set of validities? And let's suppose that we have a decidable theory, then it's not hard to see that its set of validities is in fact pi 1. And so why is that? Well, if we're given a particular schema, we can enumerate all the possible choices of substitutions, and then something's the validity of this theory, just in case all the substitutions are provable in T, or, as I say, elements of T. Since T is decidable, this just exhibits explicitly V of T as a pi 1 set, as pi 1 definable. Yes? Okay. And from this, it follows immediately that uh, the validities of T are not equal to V for any decidable theory T, because, of course, uh, if they were, then V itself would be decidable because it would be both pi 1 and sigma 1, and hence delta 1 that is decidable. So here we see that we never have the validities of a decidable theory just be the regular set of validities. So this is the sense in which if we have the theory, the theory of any subject matter is decidable, then the logic of that subject matter is not ordinary first order logic. It's not, okay. So in particular, as I say, the logic, if you like the logic of geometry, at least the first order part of the logic of geometry understood as the geometry of R3 not uh, is not first order logic via Tarski's result on the decidability of real closed fields. Okay, so we have new validities in every decidable theory, and then the question, of course, arises for decidable theories. What does this set V of T look like? Is it possible that it's actually decidable? Um, could it be complete, pi 1 complete, co-EC complete? Could it be of intermediate degree? That is in the sense of Turing degrees, might it have intermediate computational complexity? Okay, so these are questions. And we'll move on to answering these questions, at least well, as I say, we give complete answer to these questions, but we'll see how far we get with that. Okay, so let's just start with an example of something of validity in some decidable theory that's not that's not valid in the ordinary sense. So let's consider the theory of dense linear orderings without endpoints, famous, the first example anyone meets of an omega categorical theory, that is a theory all of whose countable models are isomorphic to one another. And let's consider the formula, the schematic formula for every y and z. X holds of y if and only if x holds of z. So, of course, this formula is not in ordinary parlance valid. But on the other hand, it is a validity of the theory of DLO because for any formula with one free variable in the language, either the theory proves that everything holds of this, or the theory proves that this holds of nothing, right? So, and that's just that's very clear from the rich collection of automorphisms of Q, right? So anyway, so that's yeah. So there, so there's a sense in which subject matter conditions what the validities of a given theory are. Okay. So let's now consider the question, let's start to look at analyses of complexity. So in fact, the validities of the theory of dense linear orders is computable. And why is that? Well, this theory has quantifier elimination, so every formula is equivalent to a disjunction of conjunction of clauses and of that form. And they're at most, well, yes, they're computably many easily. That is 2 to the 3 of the n squared if you count them up, a generous upper bound. And and then so then it's easy to see that we just go through the various substitutions and can compute whether a given formula with whatever number of free variables is valid. So that's straightforward. Okay. Okay. But then, yeah. So we good. Now, to proceed further, we need a famous theorem about omega categorical theories, the central theorem about them, namely a theory is omega categorical just in case for each n there are finitely many n types consistent with T. So that's a very well-known result. And that invites a interesting invariant of such a theory. That is the real Narjuski function associated to an omega categorical theory just tells us how many n types there are for each n. So that's a very kind of very significant, you know, invariant associated to omega categorical theories. And it's in terms of this that we will get a handle on the complexity of the validities of omega categorical theories. That is, for a decidable omega categorical theory, the collection of validities of the theory is actually Turing equivalent to the real Narjuski function of the theory. So I see, unfortunately, the T here is Turing equivalence. The T's there are the theory. Okay, so good. Okay, and so this is relatively anyway. This so here we can see that if we have an n-area relation symbol, uh, it the real Narjuski function applied to n is less than or equal to m, just in case uh, this sentence here uh, is a member of v of t. So basically this is saying that there are m, the m things here are things of potentially different type, and everything is you know equivalent to one of them. That is so anyway. So that's pretty straightforward, and therefore we have that the real Narjuski function can be computed from the validities of T. And on the other hand, if we have an oracle for the real Narjuski function and consider a formula, how do we figure out whether that formula is a validity, right? Well, we go through uh, so for each of these xi with arity ni, and di, the real largest, the number of types of, you know, of, with ni free variables, we enumerate the list of formulas until we find a list that represents the type. And these give us all the ni types, and then we just recognize that all formulas of that arity are disjunctions of these representations of the various types, and then we test each, uh, we test our schema with all of these possible disjunctions, and hence we can figure out if we know RNT, we know the real Narjuski function for T, then we can compute V of T. Okay, good. So, and this is just by the by. If if this is just, I think, just an interesting observation that the relation between the validity and the real Narjuski function. So if we have two theories with the same validities, then they'll have the same real Narjuski function. That's implicit in the first part of the proof given above. And then you might wonder about the converse, but that is, you know, does the real Narjuski function actually determine the validities of the theory? But that's not true. In a beautiful example given by Alex Krugman, and so consider the theories of the countable random graph and the countable random tournament, two well-known omega categorical theories. One can see that since both of these theories admit quantifier elimination, then the k-types are determined by the presence or absence of edges in the case of the random graph, and by the orientation of edges in the case of the random tournament. And from that it follows immediately that the real Narjuski functions of these two theories are the same. But on the other hand, the validities are somewhat different. That is, we have these facts about the types of pairs, and that generates a formula in view of U that's absent from V of T. So this this type these type equations just follow from the fact that we have the random tournament, right? That is, these, dealing, kind of randomly assigning orientation of edges. So that's a good example. Okay, so now we get to what is the central result that yields the classification of types for omega categorical theories, and that's the following result of Schmerl. That is, for any computably enumerable degree, there's a decidable complete omega categorical theory such whose real Narjewski function is of that degree. So that's Schmerl's theorem. And so from our earlier result, we get that for any computably enumerable degree, there's a decidable complete omega categorical theory T such that V of T is of that degree. So this just falls, out of our earlier, you know, demonstration that the validities of the theory are Turing equivalent to the degree of the real Narjewski function, and then Schmerl's result gives this complete analysis of the the complexity of the validities of omega categorical theories in terms of Turing degree. And so the idea here is that we you know we get a lot of variety in the complexity of the validities of decidable omega categorical theories. So that's good. Okay, so now we move on to non-omega categorical theories. And and here the basic theorem is that they're all the same, as opposed to the omega categorical theories, where there's a lot of variety in their degrees. Here, they they're all pi one complete. So that's and this well, okay, so now I'm wondering, looking at both the time and the I'm wondering. Okay, well, maybe I can say just a tiny bit about uh, the proof of this result. So okay, so the ideas will show that there's a pair of computably inseparable uh, C sets and a set Y separating them such that Y is computable in the validities of T, and it will follow, the result follows from this. Okay, it follows from the claim that V of T has PA degree. That means it's the degree of a complete extension of piano arithmetic. That and and then from the lemma, the earlier lemma, meaning that that lemma told us that the theory of the set of validities of any decidable theory is pi 1, so it has CE degree, and there's only one CEPA degree, that's zero jump, the complete CE set. And so from that, it follows immediately that V of T is pi 1 complete. Okay, so how do we establish the claim? Well, this essentially is a matter of encoding the computations of Turing machines in a way that's visible to any old non-omega categorical decidable theory. And maybe I think the detail of this may be maybe a little much to go over. I mean, I'm assuming that let's assume that many of you have seen uh, encodings of Turing machines. What's the difference here? The difference is that we will be making use of the fact that a non-omega categorical theory has for some n infinitely many distinct n types, right? That is, that's, the real Narjiski theorem tells us that that having finitely many n types is intimately associated with being omega categorical. So since we're dealing now with a non-omega categorical theory, we have infinitely many n types. And then the thought is we can use these n types to encode uh, steps in a compute, time steps and tape cells. Of course, it's slightly subtle because the various relation, order on the tape and procession in time, they're not actually going to be linear orders. They'll need to be pre-orders, as says here. But but that's all fine. That all works out, and in the end, we're able to do encoding of Turing machines in this way. And then once we've done that, we can you know establish establish our claim. But I think this is I see that the time is time is flowing along, and let's I don't want to. I mean, if anyone would like to explore any of that in more detail in questions, I'd be happy to do that. But I want to make sure to get to the material, the later material. So, okay, so, and let me think if I'm just looking at the time again, and I'm thinking, what I think I want to do, given the time, is even though, well, I'll, yeah, okay.
Well, actually, since you are willing to take questions on the go, maybe you can be a little bit more relaxed with the time. Don't worry. I think it should be fine. You just go. Yeah, continue and don't worry about it.
Okay. Okay. So, so maybe I will. Well, still, I can always come back. Yeah. Maybe I think I'll flip to the coda and then maybe come back for this section. Or no. Okay. Okay. I can. I can. I can do this section. Okay. So as I say, one of the the main result of this work was this, solution to this problem that Vaught posed. And so we have this, definition here of the validities common to all decidable theories. And Vaught wanted to know uh, the exact classification of that in the arithmetical hierarchy. And Cobham had showed that it was in pi3, Hanf that it's not pi1. And but then let's look at the context for Vaught's question. So we say a structure is computable just in case its atomic diagram is decidable. structure is decidable, just in case its elementary diagram is decidable. That is, the collection of formulas that are, with constants from the structure, formulas of arbitrary logical complexity with constants from the structure is true in the structure, that object is decidable. VFS is the schemata valid in all finite structures, CS the schemata valid in all computable structures, and VDS those valid in all decidable structures. Okay, so the thought is thinking of uh, all finite structures, finiteness as a kind of constructivity, similarly computability, and computable structures are in some sense they're constructive, and similarly decidable structures. Then we can think of validity uh, in these structures. And now, when I say validity here, I just mean you know truth in every structure in the given class. Not okay. Okay. So here we have these let's say various grades of constructive validity. And Trachtenbrot famously established that the finitely valid formulas, that's a pi1 complete set. So that's already, there's no proof procedure for validity of sentences in finite structures. Uh, Vaught, building on work of Mostovsky, showed that validity in computable structures is not even arithmetically definable. Uh, then Cobham and Vaught showed that, independently showed that if T is a decidable theory, then T has a decidable model, and hence that VDEC and VDS, the validities over decidable structures, coincide. And then just interestingly, in this realm of looking at, what's, what validities over various classes of structure look like, we already saw under the Hilbert-Bernays theorem that, let's say, validity over structures with delta 2 relations, delta 2 validity is exactly ordinary validity. Mostovsky had actually asked if the same thing is true for validities over Boolean combinations of sigma 1 relations. So Putnam, in a paper called Trial and Error Predicates and the Solution of a Problem of Mostovsky, actually showed that, in fact, every first order schema without identity has a model whose relations are in sigma 1 star, which of course tells us that sigma 1 star validity is ordinary validity, right? So he also showed earlier that there are schemata with no models, none of whose models are in sigma 1 together with pi 1. So that's not a class of relations. It's adequate to give ordinary validity. And I want to pause over this for. One, I want to pause over this, come to think of it, because I should say that Warren Goldfarb, again, co-author of the earlier paper I mentioned about the Gödel-Bernays theorem, also has a lovely paper on Putnam's result. It's called "On Putnam's Paper on the Complexity of Models," if I'm remembering correctly. And again, he gives a very new and very perspicuous proof of Putnam's result, and gives a lot of interesting discussion. And part of the discussion is to point out that it's still an open question whether this result holds for the predicate calculus with identity. So that's a long-standing open question whether the sigma 1 star relations suffice as let's say a, a satisfaction class of models for first order schemata. But then, thinking in those terms, just thinking about you as I was kind of saying at the outset, thinking of the completeness theorem and its enormous significance. It gives us a gigantic, let's say, reduction in complexity, or thinking. Uh, well, this notion of being uh, satisfied by every structure whatsoever, this is actually captured by some notion of provability. So what looks like some notion that's defined in terms of quantification over arbitrary structures can actually be defined by existential quantification over numbers. That is, it's a sigma 1 property. But then thinking in another way, well, we have the Lervenheim-Scullin theorem. So so who would have thought, that thinking here, well, that countable model, that is validity over countable models coincides with full validity. That's interesting. But here we can think that, oh, and it's not just over, countable structures, it's over a small sub-collection of countable structures whose relations, right, are of rather low complexity. Not like super low complexity, meaning not computable, right? But whose relations are in sigma in sigma star 1. Okay, but then thinking in another, in the direction of abstract model theory and things like the Lindstrom theorem, we might wonder if it wouldn't be interesting to look at refinements of this sort in the context of abstract logic. That is, okay, there's the Lervenheim-Scullin theorem, but how about complexity refined versions of the Lervenheim-Scullin theorem? So look at a logic that satisfies the Lervenheim-Scullin theorem, different than first order logic, and ask about what complexity of relations is required to satisfy sentences of this logic. So I think there's a kind of interesting area to investigate in that direction. Anyway, so moving right along. Um, so as I say, we were able to resolve Vaught's question and show that the validities of all decidable theories are pi3 complete, and here's the argument, very abbreviated. I should say, this relies on you know various results about effectively closed subclasses of 2 to the omega. So okay, so let's look at we have the ETH tree, in determining a pi1 subclass of 2 to the omega, and then we have an enumeration of the language of graphs, formulas in the language of graphs. Then there's a a result of Hanf and Peretyatkin, that there's a computable function that for each e, uh, you know, uh, gives us a sentence in this language such that the complete extensions of this, this this sentence theta sub sigma v has a decidable complete extension just in case the ETH tree has a computable path. Right? So that's a result of theirs. Now, uh, Martin and Geisarch had shown that the set of V such that T sub V has no computable path is pi3 complete. Uh, and there is, on the other hand, we show there is a computable translation from the sentences of L from the language of graphs to a schematic language, meaning sentences in the pure predicate calculus without identity, such that theta has no complete decidable extension, just in case the negation of the translation of theta is a validity in all decidable theories, and then it follows immediately that this gives us a reduction of this pi3 complete set to VDEC, and that together with Cobham's result that VDEC is in pi3, that's the theorem. Okay, so now Uh, and so there remains an interesting open problem that was also, it's stated in um, in Vaught's paper. That is, how about the validities common to all finitely axiomatizable complete theories, and is that pi3 complete? And so far as I'm aware, that's still open, right? Okay. Okay. And I should say that these questions were first, considered by, Tarski himself and by Tarski and Vanda Shemilev. So these are very much in the orbit of Tarski and his students. So, okay. So now to the the coda, that is now for something completely different. Okay, so we have a structure of finite signature, and we say, when is the first order theory of this structure decidable? Well, that's, we all know the answer to that question. When there's a two-valued Turing computable function, such that for every first order sentence in the language, it tells us whether the sentence is true in the structure, right? Yeah, but that, sure, but is there some other way of characterizing this that is doesn't involve any reference to sentences and any reference to Turing machines, right? Yeah, that'd be good. And I should say that this is very much in the spirit of this, of a lot of Tarski's work. That is, uh, asking whether various logical notions have, as it were, mathematical characterizations. That is, characterizations that don't refer to language, that refer to intrinsic properties of, structures. So, famously, he gave characterizations of classes of structures that are, closed under substructures. That is, anyway. So so that this is a big theme in this book of Juliet Kennedy's that I mentioned earlier, that I have, oh, or did I, or yeah, yeah. Oh, no, maybe I haven't mentioned that
Yeah, yeah,
yet.
you
So
mentioned it. You mentioned it. It's called.
great, great. Thank you very much, Guillermo. So good. So, anyway, so this is very much in this question is very much in the spirit of Tarski, right? And here, just as a cultural interlude, and this is a quotation that, well, many people have made much of, but Juliet, in her book in particular, takes this as a as a jumping off point, and rightly so. Um, you know, this, I find this, I'll let you guys just read it for a minute. I find this very, very, very moving and apt, right? An absolute definition of an interesting epistemological notion. So, it's, not really, I, 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 no, anyway, when I teach this nowadays, it's like, so it's not that it led to the invention of the iPhone, right? It's rather that it gave an absolute definition of an interesting epistemological notion, and that strikes me as about right. Anyway, so yeah. So here we go. So a structure is finitely axiomatizable, just in case its first order theory can be axiomatized by a single sentence. And it's an immediate corollary to the Gödel completeness theorem that if a structure is finitely axiomatizable, then its first order theory is decidable. Okay. And in virtue of the work of Ehrenfeucht and Froussard, both elementary equivalence and quantifier rank n equivalence have purely combinatorial characterizations, uh, but the structure is finitely axiomatizable just in case there's some n such that any structure that's n equivalent to A is fully first order equivalent to A. So uh, we can characterize finite axiomatizability in a formalism-free way, that is, without any reference to syntactic objects. So here, this is just a purely combinatorial condition on the structure A. And this tells us whether or not A is finitely axiomatizable. And so this notion is, has we might say you don't have to know anything about language or logic in order to understand what finite axiomatizability means. And anyway, there we go. Okay. So how about, and but of course there are many structures with decidable theory that are not finite axiomatizability. So good luck giving a combinatorial characterization that captures them, right? Okay, but here's the question: is this an unpromising example? Let's see. So we have the structure, the integers with successor and order, and this is finitely axiomatizable, but its reduct is not finitely axiomatizable. Okay. Nonetheless, it does follow immediately from the finite axiomatizability of this structure that the first order structure of its reduct is decidable. That's easy to see. Okay, so can we somehow ratchet that, you know, unpromising example up to something more promising? And so let's consider a structure of finite signature sigma and a binary relation symbol not in the signature of that structure. And we'll say that A is finitely axiomatizable by graphical expansion, uh, just in case there's a first order sentence in the language with this extra binary relation symbol, such that for every sigma structure B is elementarily equivalent to A, just in case there is an expansion of B to this expansion C of B to this new signature, such that C satisfies sigma, right? Okay. So this, yeah, so this, yeah, this is good. Yeah, where, yeah, so yeah, so some, yes. Anyway, so I hope this is clear. And just as was the case in the unpromising example, it's easy to see that if a structure is finitely axiomatizable by graphical expansion, then its first order theory is decidable, right? Okay, okay. And moreover, combining again the results of Aaron for say, now with results of Hinteke, it follows that this condition is equivalent to a formalism-free condition, right? That is, we have no mention of that is when I talk about the result of Hinteke, that's Hinteke's the games for satisfaction of formulae. So, again, another shout out to a great book that covers all of this and so much more is Yoko Vaananen's book on games and logic. I think it's a wonderful presentation of all of this stuff. Anyway, so we have here a formalism-free condition, this graphical expansion. Okay. And now we have a theorem that structure of finite signature, its first order theory is decidable just in case if it's finitely axiomatizable by graphical expansion. And this is just a direct corollary to results of Craig and Vaught, finite axiomatizability using additional predicates. So I find this quite fascinating in the sense, so clearly this condition it's not, is formalism free. It makes no reference to, formulae via, the results of Erfurt-Froussay and Hinteke. And moreover, it makes absolutely no mention of machines, right? So it's the property of a structure, a structure is it's a mathematical object. The property of a structure of being, of having a decidable first order theory is just it's just a combinatorial property of the structure. It may, making no reference to language, making no reference to computation. So in a one might try to make of this some way of addressing the so-called encoding problem for talking about computability. That is, well, we have many different ways of encoding things, and with respect to some of them, things will look computable. With respect to others, they won't look computable. And you might say, hang on, here we have the notion of the decidability of the theory of a structure is purely combinatorial. This this purely combinatorial condition is not looking at encodings of anything, right? No, yeah. Anyway, that's it, let's say by the by. But anyway, thank you so much, all of you, for So this is the end of the coda. So thanks so much for your attention to this. I really appreciate the opportunity to talk about these things, which, you know, anyway, thank you. Thank you.
Thanks so much, Scott. Thank you. That was a lovely talk. By the way, just a very small